Let's get started. So I don't think I went over all of the programming assignments for this course. Does anyone want to see the programming assignments? Anyone have any questions about the programming assignments? We have 5 of them. I went over the first one. I remember that one. The first one, okay, I'm going to go over them anyway because I'm not getting any responses. Hello? Hello? We're going to start. Thank you. You can take it outside if you want to continue. I just can't talk over you. Yeah. Oh, okay. Okay, so we went over program number 1. That was the beginning of the course. That was that Julian date conversion, and that was a function, was the goal of that one. And then programming assignment number 2 was about classes, and we created an employee class. I believe I went over that one as well. And in the employee class, we had to set certain methods, and we had certain data members that we needed to, and it was an orientation to classes in general. And then we had assignment number 3 that I think I can't remember if we went over or not. I think I might have, but I may not have, actually. It had to do with structures, and it gave you a template for a structure. And this one was twofold. It talked about structures, but it also talked about pointers and the use of pointers. And that lecture that I just went over when I talked about pointers recently, that pointer lecture is going to give you everything you need to know. There's also another pointer lecture, which I believe is lecture number 11. And lecture number 11, hello, here it is. It's about, it covers chapter 15 of the text that I recommended for this course. That's going to get into pointers as well. And I took a little survey before I started here, and nobody wants to hear more about pointers. So, I don't know, I guess. So I'm not going to do pointers today, but I already did pointers. But if you're having problems with pointers, lecture number 11 is going to be a good resource for you. Especially for that assignment, it might actually help you a little bit. The assignment has some sample code that goes with it. And here it is on the bottom. Purposes experiment with C++ structures and pointers, and you're passing, I believe you're going to use a function for this, and you're going to pass some information to the function, and you're going to use it implement the dot notation with this arrow instead of the dot because it's a pointer, and you're going to essentially work with some of those concepts that we talked about already. The one that I think we should probably go over would be this one here. This one is about the dinosaurs, and this is a true inheritance example. So the first part of it's not a big deal. It's just creating a class. You're creating a base class, a generic dinosaur. And in the dinosaur, you're going to use the base class, and you're going to make some classes from that, some subclasses. And you're going to create an apeirosos, whatever you call it. I can't pronounce these. You're going to create 3 other dinosaurs that are going to have 3 other characteristics. And you might find that you're going to want to use the multiple files, as I talked about before, the .h's and the .c++ files, but you don't actually have to. You can put all this stuff in one file if you want. And the purpose of this is to basically learn how to do the inheritance. And it's a very simple example of creating a base class, coming up with 3 subclasses. We're going to create different specifications of more advanced dinosaurs. One of them is going to be able to eat, and one of them is going to be large, I think, and one of them is going to be a fast runner, one of them is going to be a slow runner, characteristics like that. Once you've created them, you're going to write your own little driver program. And your own little driver program is going to create some instances of these dinosaurs so that you can see them work, see them run. So I actually think that this one is probably the most difficult assignment. I don't know. Only because inheritance is one of those kind of interesting things to see happen and to actually get to work correctly. But there's a ton of inheritance examples on the internet. Actually, none of them do dinosaurs, which is good. But if you go through that inheritance lecture, which is, I believe, number 3 that we're going to finish today, you'll kind of see, oh, maybe this one's the hardest one. You'll kind of see how the inheritance works from a syntactical point of view. The last assignment for this course, number 5, and there's only 5 assignments for the course, by the way. Number 5 is to look at this linked list, and we talked about linked lists last time. I believe that was the focus of last week's lecture. And we looked at, and this one's going to give you 2 files. It's going to give you lllist.h and lllist.c++, and you're going to implement a couple of methods in here, and the methods are going to be to add a single node and to delete a node. So you're given the list, you're given the nodes, you're given a working program that hopefully you can get working. And you're going to download these from bhacker.com. If you go in and you take a look here, if they're not in the EMS, which they probably aren't actually, you go in here and you look at where the assignments are located. You'll see this is where the C++ LLlist.C++ and the LLlist.h is located. And you'll also see over here, these are the samples I gave you for assignment number 1. So the support files are here if you can't find them in the EMS. And you're going to need these 2 files because you don't want to reinvent the wheel. And what you're going to do essentially is make some modifications. You're going to add the code to print out the linked lists, which is a loop. And you're going to add the code to do the add, and you're going to add the code to do the delete, essentially. And if you remember that lecture that we went through, which is the one we're going to finish today, I believe. Was it lecture 3? I don't remember. That had the linked list? I think I just covered it last week.
83.
It was what? 83. I know this is the slide we ended on.
Yeah.
But I was going to say, before we got to slide number 83, I think we covered linked lists. Yeah, but actually we're going to see in a few minutes here because I'm going to go through it. Last week, and this is going to tell you where to find a code for that number 5, for assignment number 5. We talked about this whole lecture is going to be good for the assignments, actually. It's going to talk about the concept of creating the class, the constructor for the class, the driver program, the skeleton. And remember, we inherited classes. This started out with our entire class discussion, and I did this a few weeks ago. It also covers pointers as a concept as well, and the differences with the dot notation and how to use pointers to resolve the operator. The concept of the accessor and the modifier was also covered in here, and the use of the different files. And then we talked about inheritance in this particular lecture. It's like 160 slides or something like that, or 60-something slides. It's pretty long. And this is where you're going to get the information, where you're going to kind of use it as a basis, I hope, to create your dinosaurs and your 3 inherited dinosaur subclasses. And overriding methods, public and private, and stuff like that. And then I have to go through all this. Let's see. And then we talked about object-oriented programming, a little bit in terms of the object, creation of the object, information hiding, inheritance, and define some of these terms. I'm going to talk a little bit more about object orientation today. Talked about the scope as well. This wasn't the linked list one, so we had a different lecture then that covered the linked lists. I can't remember which lecture that was, but it was last week's, so you can probably find it in the archives. I know I covered I know I covered structures as nodes inside of a class list, and then there was also examples of classes of nodes that were inside of a class list as well. And in there was methods for adding items, adding nodes, removing nodes, printing nodes, and stuff like that. That's where you're going to get the source code. The answer to assignment number 5 is in that lecture, but I can't. So I'll leave it to you to find it then. Go through the archives of the lectures, and you'll find it. It's probably going to be towards the end, is what I'm thinking. But it's definitely going to help you with that assignment. So. All right. So continuing onward. I was talking about object orientation, which is what I want to finish up with today, and then go over the object-oriented lecture as well. Classes and files in terms of the relationship. I think I stopped here at static methods. So we have a concept called static and class, or class methods and instance methods, class method, data members and instance data members. And I'm going to talk a little bit more about that in concept in a few minutes, but as a static method, what we're doing is we're making a class method, and we implement it by a static method. So static method is a class method that can be called without having an object created of that. So just like in Java, where you can create a class, and the classes can have methods inside, and we use the keyword static next to them, actually, and we create these methods and these data members that can be changed and altered at the class level instead of at the instance level. Normally, as we've seen so far, we make instances of these objects, and a class is a template for the creation of an object. When we create instances of the object, we have dog 1, dog 2, dog 3, and each one of those dogs has their own instance variables and instance methods. So the static methods are they create the class level variables and the class level methods. So it affects all of the dogs at one time instead of just each instance of the dog. So you have to use the scope resolution operator, which is this one here, to identify the method. And the method can't access non-static data members. Everything that's static has to be used together as static, which is kind of different than Java. I believe you can access non-static data members in a static method in a Java program. They don't exist unless you have an object created. So non-static data members don't actually exist until you create, in C++, until you create an instance of an object, and then you have an instance method, instance data, I should say. So in terms of the static data member, it's possible to have a single variable that is shared among all the different instances of the objects. This would be like the number of dogs that have been created. And so all instances are sharing the same variable. That's a static variable, or that is what's called a class. We use the keyword static to create the class level variable. So we declare the variable as static, and we use the keyword static when we declare it. So the data members that are static must be declared and initialized outside of the class at the global or file scope. So we say number of dogs is equal to 0, and then we can change the number of dogs outside of the instances of each one of the dogs. And then each instance of the dogs can go back and find out how many dogs are there at any one moment. So here's our class foo, and inside we say static integer count, or CNT. And then out here we can go count plus plus inside a method, or inside of a class here. We can do this actually anywhere we want to. Or excuse me, count, or wherever to go. Here it is. We're printing it out to the screen. This is foo count. This is a different count, plus plus. So we're keeping an instance, and we're also keeping a class method going on here. So, but I wanted to bring that concept up in terms of how you are going to use the keyword static. It's to basically create a class versus an instance, method, or data member. So, and I'll have another example further on to show you that as well. So we have a problem. Class definitions usually have a .h file, as we've seen so far. We have iostream.h, stdio.h, a bunch of h's that we use in programming in general. We have cdog.h, and all the classes that we create ourselves have a template kind of description or definition class. And then we can also include them in other C++ files. We can put as many .h's as we want in any program that we want. So we can't declare and initialize a static data member in a .h file. It has to actually go in the .c++ file, because then we wouldn't know which class it belonged to. So in terms of the solution to it, if we say foo.h, we've got foo C++, f1.c++ is including foo.h, f2 C++ is going to be including foo.h. If we have this here, it's going to say, oh, it's already included. The compiler is going to come back with an error message and say, foo.h is already included. You're including it multiple times. So we can essentially put in an if defined in statement at the beginning to get rid of that problem, and then we can essentially not have to worry about it. And also, if we're going to use a static method, we can put it inside of the foo.c++ file instead of putting it in the .h file. So we can have a static integer. This is going to be a problem here. So the solution is essentially put it inside of the C++ file instead of putting it in the .h file. That way we don't have to include it. We talked about one of the examples. We actually had a operator overloaded. Actually, that was in the linked list example. We overloaded one of the operators to print out the linked list. And you can do that essentially in that assignment if you want to as well. Use the same techniques. So you can define for some of the C++ operators, any one of the operators actually. You can apply a different meaning when it's used with an object instance versus a variable, which comes in handy. So here's a vector example that defines an in-stream and an out-stream using the redirectional operators to a plus and a minus essentially. And it changes some of the other definitions as well. So operator overloading, you can't define completely new operators, but you can take existing operators, like these are the operator symbols I'm talking about, and you can redefine their meaning so that the behavior works appropriately for the particular instance that you're working with in terms of the variable or whatever it is you're trying to print to the screen. So you can redefine the meaning of the operator on a built-in data type like integer and double as well. Not recommended. Causes confusion. People overload operators and then you use a plus and you go, oh, it's supposed to be doing plus. Why is it doing concatenation or something? And then all of a sudden the meaning changes. You can also change the operator precedence and also the associativity. You know, is it going left to right, right to left? Is it doing inside the brackets first? So you can modify C++ essentially to customize the behavior to meet your own needs. We also have the concept of inheritance that we looked at in terms of the object-oriented features, because this lecture is going through all of the object-oriented notions. Inheritance can create a new class that inherits from the existing class, as we've seen so far. Add new methods and members and methods to it, and replace the methods by overriding them. So we can specialize. So the terminology actually being used is really referred to as a specialization of an existing class. So in terms of the terminology, what exists is the base class, which is the original class, and then we have the new class called the derived class. More terminology. So objects of the derived class are also objects of the base class. So it's just, then you can have the super and the sub as well. So here's an example. And this is kind of like your dinosaurs, sort of. You have a base class called shape, and then the shape represents the abstract notion of a shape. And then we can derive shapes from this, and the derived shape would be rectangle, circle, triangle, all sorts of different types of shapes. So the object that is a circle is also a shape by concept. So we have public and private, but we also have this thing called protected. So we had protected class members. Protected members means that the derived classes have access to the data members and the member functions, but otherwise the members and the data members and member functions are private. So protected makes inherited classes that are used in inheritance, makes that information visible, but it still makes it not visible for the public. If it's private to everybody. So usually we have public inheritance that goes on. So public, private, and protected inheritance change what the members and the methods can access outside of the class. So usually we want to keep things public if we're going to inherit it. Makes it easier. And now we have the concept of polymorphism as it's implemented in the language. So we can treat derived classes as objects of the base class, which means they're polymorphic. They can be a circle but also be a shape. So we can kind of change back and forth. So the problem is that when we're doing this, we don't get access to the derived class methods, especially if we're overriding them. So we can complement them. So we have this thing called a virtual function. Don't have this in Java. It's definitely particular to C++. So a virtual function is a method in the base class that can be overridden by a derived class method, which gives us our behavior of overriding. When we override, we get rid of the polymorphic behavior because a circle can't act like a shape if its methods and data members are overwritten, and they become more specific to be circles. So as an example, we'd like to have each object to know which print method it's going to use. We declare the base class print method virtual, and this happens essentially because now we know each object that defines a print function, so a print circle and a print shape, are going to have two different functionalities to it. We define the method as virtual, which means it can be overridden. So that was everything you ever wanted to know about those features. Lecture 11, as I mentioned before, was on pointers. Just so you know that lecture number 13, I'm just finishing up the last bits of the lectures for this course, because this is our last lecture day. Lecture number 13 is on the concept of recursion. We don't have any assignments on recursion. Recursion is kind of like one of those things that's hardly ever used, unless you have to. There are some solutions that lend themselves to recursive solutions, some that, are more bothered. If you're not familiar with the concept of recursion, it's like iteration. It's in lieu of looping. And most people consider recursion in terms of functions. So a function that calls itself is recursive. And then each iteration calls itself. And then eventually it has to return back. So that kind of behavior is what's referred to as recursive behavior. It's supported in a lot of languages. It can get kind of hairy. And you can replace it with regular old looping if you wanted to instead. Most recursive solutions can be done in loops. Only problem is sometimes it's not quite as easy to comprehend the concept. Sometimes the concept's a little weird. Let's see. I wanted to see what was in 14. Number 14 is an object-oriented design, inheritance, and class example, which is also going to help you with that dinosaurs program. It goes through a couple of different examples, and these examples here, I believe, are at the bhacker.com. Let me just make sure, actually, now that I'm looking. Class examples. Yep, here they are. Well, we just saw a few minutes ago something about vehicles and cars in this lecture here. Whoops, this is number 3. We don't want number 3. This one here, car.h and transport and vehicle.c++ and vehicle.h. Those files that are mentioned in that lecture can be found right here. So not a bad one, because you could essentially, not to give this assignment away again, but you could essentially, this is dealing with creating a base class called a car. From a car we're deriving a truck and a vehicle and a car. Or no, I'm sorry, the base class is vehicle. We're driving a car and a truck and what's this, transport? I don't know. We're driving some classes from a base class of vehicle. We're making different types of vehicles, okay. Kind of like making different types of dinosaurs. So we'll have a dinosaur, which is going to be the vehicle, and then we'll have, instead of a car, we'll have a Tyrannosaurus or something, or a Hexosaurus, I don't know. 3 different kinds of dinosaurs that are going to be printed from that. So you could theoretically take this and change the theme to dinosaurs if you get stuck. And then by doing that, you're going through the example. If you're going through the example, then I would actually look at the lecture that's associated with it, which is lecture number 5. And it will teach you in the process of doing the assignment what the inheritance is all about. So that's not a bad, oops, not a fine, no, not number 5, it's number 4. As I misquote everything. It's assignment number 4 that deals with the dinosaurs. To also mention, the linked list examples are here. So if you're thinking about getting some extra help on being able to add a node and remove a node and print a node, I guarantee it, you can find it in one of these examples as well. So this is probably easier than surfing the internet and trying to find sample code. I'm actually giving it to you. And the dev files are dev C++ files for C++. So they'll actually, there's a whole project here that you can load up, actually. And the linked list examples are coming from that linked list lecture. The inheritance examples, these are going to be your examples of a class and class variables and class methods. And if you look at the examples, you'll see the keyword static being used here. So we can run, and you'll see out here, actually this is a good example, because I just mentioned it. Inside of the class, myClass, I created a static method, and the static method is called void say hello. And then I can run void say hello, and void say hello is going to print out hello world. And I can run myClass colon, say 2 colons for the scope resolution, which is the syntax you have to use for this, say hello. You can also do this with a data member as well. So you can keep a counter, increment the counter, run a method. The trick and what you're looking at here is that we have never created an instance of this class, which is why they call it a class member function or a class data member, because you're running it at the class level, myClass. I didn't say, my class is equal to, new myClass, and I didn't run a new myClass dot say hello. Instead, I ran it this way, so I didn't create any instances of it. And that comes in handy when you want to, I don't know, keep track of all instances or do something interesting at the class level. And the same example here is extended to the method concept, or excuse me, to the data member concept. So in here, I have, oh no, that's the same one. Oh well. Here it is. Different example on the data member. So here I have a static integer I. This is our static data member right here. And then down here, we're saying class, myClass colon I is equal to 3 outside of all of these instances. And so if we asked, c.test, and c.test is printing out the value of I, it's going to be changed to 3 for all of those instances. So class variables, class methods, change information for all of the instances that exist for them. So it's interesting. So you can control all classes, all instances of the class at the class level. I said that right, good. So let's see, going just to complete our tour here. Miscellaneous examples is going to be, this is going to be recursion actually, I think. I know it's going to be some question number 2. This is question number 2 here. I don't know. It's going to be related to some of the lecture material. We'll actually have some of the examples in here. I believe that's a recursive example though. And so we've actually, after today, we've actually covered everything except for lecture number 14, which I'm going to leave to your own likings, and number 13 that covers recursion. And I don't believe I'm going to put the concept of recursion on anything. Next week we will have the final exam review, and I'll tell you exactly what you need to study. But I can tell you right now it's going to be multiple choice. And it's going to cover concepts such as classes, inheritance, class members, static, using the word static, what that's all about, object-oriented techniques, inheritance, based on the assignments and based on the lectures that I did go over. So. But I'll have definitely a lot more details for you next week. So this is 95 slides. Not going to take us that long, because I've actually covered most of the stuff already, and I'm kind of going to use it as a class review. So it's a nice conclusion lecture, actually. So what are we looking at? We're looking at the object-oriented software development features. It is actually chapter number 14 of the text, which is towards the end. And the concept of the design, in terms of what we're doing with the C++ coding, because as I mentioned on day number 1, we can program in C or C++ without using object orientation. There's, we can just use procedural, we can use functions, never create a class. Until we create a class, we actually haven't used any object-oriented features. Not like that in Java, though. Java, you have to create a class in order to do anything. So in terms of the technique for developing a solution that's expressed in terms of self-contained objects, the object, or the, I was going to say, they're going to keep talking, we can shut the door. Oh, no, they're done. No, they're done. So, oh, okay, you can shut it anyway if you want. So, in terms of object-oriented programming, the programmer thinks in terms of defining attributes and behaviors in objects, and then models the real-world entities. So we have different approaches than regular C. And this should look familiar. Reasons for object orientation, it's a PI, abstraction, polymorphism, inheritance, and encapsulation. Those are software engineering issues that we've covered in this course, actually. We learned about the class, and the class concept and the pattern of instantiating an object of that type. Class generally contains private data and public members called methods. And in C++, a class is an object type. We only have one object type, actually, that we create user-defined. Other classes can create objects. So we have the string object, which is another object. And we have built-in methods that we run on the string object, as we saw in another lecture, where we can find a string within the string, a substring. We can find the length of the string. We can run a bunch of methods on there to manipulate that object. So we have more than just user-defined objects, which is an important concept to remember. When we create a definition of a class, we're defining the attributes and the behavior for that new particular type, just like any other abstract data type that we're creating. And remember, we started out with structures. The difference between a structure and a class, pretty much the same concept, except for classes came after structures. And classes have inheritance and reuse and a bunch of other object-oriented terms. And a structure is really kind of a non-object-oriented version of a class. It's made just to hold, groups of unrelated or related but different data types, different pieces of information, complex data together into one concept. Attributes are the data members, the behaviors are the member functions. We create instances of classes. It's called instantiation. Going through this kind of fast because it should be a review. If it's not, download the slide set, go through it on a slower pace. We have the concept of a superclass and a subclass, meaning that the class that's being inherited from is the super. The class that inherits the properties is the sub. A super can be a sub can be a super. There's no restrictions. They can have multiple rows. In terms of defining objects, the object-oriented program consists of a bunch of objects. We define them, and they have 3 different characteristics: identity, state, and behavior. And this is the part where I said if you took my Java course, this is a redo. This is where you're going to get bored. The identities, the states, and the behaviors are the 3 different characteristics of particular objects themselves. What is meant by these 3? Well, the identity is the name of the object. It's an employee, it's a car, it's a vehicle. I was having identity issues earlier because I said a car was a vehicle, or a vehicle was a car. And I had to think about it and go, well, no, vehicle is just the base. We have different types of vehicles. We have cars, airplanes, boats, you know, so those got different types of vehicles. And have different varying numbers of wheels and stuff like that. So failure to recognize the differences between the names of the objects and the objects themselves can cause a problem. Is it a print object? Does it do scanning too? You know, or does it just do printing? So sometimes you get these behaviors that happen inside of classes, and you wonder, why do they call this a print class when it's scanning? Like doing something different. So the state is the data members. It's the variables, the properties, the variables, the information that's being held, or the data that's being held about each instance. And as we've seen before, we can keep them at an instance level. We can also keep them at a class level. The behaviors, or the states themselves, are properties. As an example, the properties for an elevator might be elevator traveling up or down. So the direction of travel, the vending machine, how many coins is accepted, clocks indicating the current time on a clock. So some values that might be associated to some of the states are going to be, as an example, the current floor, number of coins, number of minutes, something of that nature. And then we have the behaviors. Behaviors are what the object is meant to do, which is our member functions. So, or our methods, we call them that. So they're the operations that we perform on the class. Instances of the class, or the objects, and we say, you know, my class.print. That's a behavior to say, print yourself. So, as a classic example. So classes themselves, we have the definitions, or the blueprints, which are the .h files, and then we have the specifications, or the implementations, which is the .c++ file. So we're going to go through a little example about cars. And we're going to make some cars and some instances of these cars and put all the pieces together so you can sort of see what is meant by object orientation. So to make a car, a manufacturer must have a design for which to build the first car. And then once they build the first car, you can build subsequent cars from that design or that model. And we would first create an object, call it a car, which is going to be an instance of this particular class. So we have a class definition called a car. And we can think of a car as, in this particular example, we're going to use Audi, BMW, and Corvette. It's the different types of cars. And so we can actually create 3 different instances, and we can call them Audi, BMW, and Corvette. So notice that all of the objects are the same type. They're all of the object type car. What ends up happening, here's where the confusion comes into play, is you've got all these objects, and you don't remember what type they are. So the naming conventions are actually kind of interesting. You know, people come up with different names for these things. In fact, sometimes they'll use the same class name, like my car, class car, my Audi, my BMW car, my Corvette car. So you can remember what the object is. Because if you can't remember what the object is, then you can't remember what kind of behaviors and what kind of states the object's supposed to have. Because those are the 2 things you need to remember about it. It's kind of like how people don't know that a string is a string. It's a string object, so they can run methods on the string, but they don't realize they think it's a character array or something, or they don't understand that there's methods associated with it. So classes and objects. The object is an instance of exactly one class. In C++, we have single line, which means everything that comes from one, with multiple inheritance. So an instance of the class is an object that belongs to a particular class. So the Corvette is a car, so the Corvette belongs to the car class. And then we have classes. Once a class is defined, it can create many different instances. So creates that ability to specialize. And objects from that class would be very similar. Since a blueprint is completed for the 2004 Porsche 911, the blueprint is for the assembly line for many instances of 2004s, 911s. We can make as many instances as we want. We can make more than one instance of that particular class. So think of it as mass production. Create one class and create mass-produce instances of that class. So in terms of defining the class, we look at the properties and we look at the behaviors that are associated to it. And then we consider these instance variables. For each one of the instances of each one of these cars, what do we want to keep track of? Maybe the gas level, maybe the speed associated with how fast the car can go, maybe the number of doors, maybe some characteristic that we want to keep track of. And here's an example of maximum speed. So these are what's called the instance variables. We have the car. It has a maximum speed instance variable that here for the Audi we have it set at 155. Well, this is telling us that the BMW is the fastest car because it goes up to size 165. And I'm not sure these values are actually true. Who knows? They're guessed. They're made up. And the Corvette maximum speed is 145. So each one of these instances has a different value associated with maximum speed variable, which is an instance variable. Then we have class variables. And as I mentioned before, we saw it with the keyword static. We create a class variable. We could set the maximum speed. Let's say we live in the state of California and the maximum speed on the freeway is what, 65? Depends on which freeway. All right, let's go to maximum 70. Well, all right, the average traveling speed, 85. So we can set it. So in this particular example, we're going to be extremely lenient. We're going to say maximum speed is 155. So now we have a class, but then we also have, we have an instance, but we also now have a class variable in here where we can automatically set 155 as the maximum speed if we want to for all of the instances, and they would all share that value. So class variables are also used to keep track of how many instances, let's say, that we're going to have of these cars. Because we only have a garage that's big enough to fill 3 cars or something. That would be a pretty big garage. So we can't make more than three car instances. So as an example, let's create a counter that records the number of cars that are going to be in the garage. Number of cars here would be 3. And this would be used the static keyword on number of cars, and we would keep it at the car level, at the class level. So imagine, you can probably think of it this way, if you're going to get at the variable content or the variable, you're going to change the variable from each one of the instances, then that would be an instance variable or an instance method. If you're going to do it from the class, then you got a class method or a class variable. And so the only difference is if you want to make it a class, you use the keyword static. And now it's a class level. Anything else, by default, it's always instance. Because theoretically, we're making this as a template or a blueprint, and we really want to edit these guys. We're trying to control these instances. We only have one of these. We got 3 of these. So this is where we're going to keep all the data separate. So. Messages. Another word for methods. Another word for behaviors. So we have turn on hazards as an example. And we have objects speak on the left and humans speak on the right. The humans would say, who's the message for? What do you want the person to do? What information do they need? That's equivalent to the object to whom the message is going to be sent to. What object are you going to call this method on? And the name of the method that the object is going to execute. And what parameters? The methods, if you know so far, are function calls. And we learned so. We're creating a function, essentially. And functions have a name, and functions have parameters that we send to them. So in order to process a message, an object needs to have a method that is defined to request the task. So the method is a small little piece of code, a function. So in the previous example, we needed a method to turn on the car's headlights. So now we have one, turn on headlights, turn on hazards. So over here we say Audi 6, if this was the name, dot turn on hazards to run the method over here. If it was here, BMW Z3 dot turn on hazards, as we see. So we've defined that method. those are considered instance methods because they're run from the instances that were created, preferencing the object name dot, the method that we wish to run. And so it's only going to affect, and it's only going to be running on that particular instance. So here we have add gas with an amount. So we can add gas, different amount here, different amount here, different amount here. We didn't put it on here, but probably the fuel tanks are probably different sizes for each one of these cars, maybe, if we wanted to keep track of that. But here we're just running a method called add gas, and we're giving it the amount of gas to add to each one of the cars. So if we add gas to the Audi, it doesn't affect the Corvette car. In terms of the method, it's also possible if you want to get the information out of it, return information. This is where we're getting into the concept of the accessors and the modifiers. We can access method. Here we're modifying because we're setting the gas amount. We can also access, get the gas level. And then we can know that we need to fill the gas. Because why are you going to take a full car to a gas station to put gas in it? You're not going to. Instead, you're going to say, you're going to look at the gas gauge and go, oh, look, I'm empty. You know, that's what that yellow light's supposed to be. It comes on your dash. I usually wait till yellow light comes on, although I hear you're not supposed to. I hear you're supposed to fill it before that light comes on, usually. But long story short, it tells me that I'm accessing information that's telling me that I need to go do something. And the method I'm going to do is going to get something, and then I'm going to modify something. So that's where the terminology actually comes from. So here we have a get gas level from the gas level, add gas, turn on the hazards, get gas level. What we saw already have been what's called instance methods. We also have class methods that work on a class level. Class methods manipulate all of the information about all of the different ones. So if we were making these cars and we were going to store them in a garage, we would have to know if the car was in or out of the garage. And we can keep track of that at the class level. And so each time we move a car in and out of the garage, we need to add and subtract one of them to the cars in and cars out. So the class itself knows how many cars are in the garage and how many are on the street. Then we can get the number of cars. So here we have here at the class level, we've got the in and out, car in and car out. Same thing as the methods, the data members or the data that we were changing, but these are member functions, methods that we're running at the class level. So car in, actually put all the cars in the garage, take all the cars out of the garage. And so we can run them to manipulate the car activity from a class level. So when we're running object-oriented programs, first one is we define this particular class, like the car in this particular example, and then the program is running, then you have the instances of these particular objects that are created, and we're manipulating the instances. Believe it or not, that's the definition of object-oriented programming. That's all we're doing. And if we can actually take an entire program and write it in this fashion and not use any other style, not use procedural, we don't call any functions, basically don't use any other methodology. And it works, actually. It works as a pretty good model. And it's easy to maintain the program this way because it creates what's called modularity, where we have a car class, we have other types of objects that we might have. And each one of them is a separate component, and we manipulate the separate components, and then we can reuse them. Take them out, use this car class in another application, put a new car class in there, change the modules around. And we have these encapsulated kind of objects or modules. And the concept of information hiding comes into place because we have this public interface. And as long as we keep the public face the same, it doesn't matter which object we're using. So we can have an upgraded car class, like a hybrid car, and put that in there. It doesn't use gas, it uses water or air or something, or electricity, and run methods on that one. As long as to get gas might be an issue. It might have to be changed to get electricity instead of gas. But all the hybrids are still using gas. But we might have to add something to it to specialize it. But in terms of information hiding, the interface to the class is the list of the public data members and the member functions. So everything that's public is what's considered the public interface by definition. And it's what we're going to make visible to the outside world. And the implementation of the class doesn't matter outside of the class, only the interface does. This is how we can use classes like IOStream. We can, include IOStream.h and use classes for cin and cout. Nobody really knows how cin and cout is implemented. Doesn't really matter. But every single version of C++ has its own implementation of cin and cout. The public interface is the same. We use the class the same way, same as the string class. We create objects of string the same way, but we can upgrade the implementation, improve the process, make it more efficient, add more methods to it. I don't know. Substitute it with another class, and the same existing methods should hopefully work properly. So, in terms of the information hiding the concept, nobody can change the implementation, and nobody really cares as long as the interface is the same. We use cin, we use cout, it works. What do we care? So you can use other people's classes without fear, hopefully. And then we have a polymorphism that we're building into the concept as well. The ability to have different objects that respond in the same message in different ways. Cin and cout is a really good example, actually, of polymorphic behavior. Because when you cin, or in this particular example, we're seeing out, we are printing to the screen I, which might be an integer, doing to a double, a string, a float, polymorphous, a poly instance of a class or something. So that's what's referred to as polymorphism, the ability to respond in different ways. And then inheritance that we've seen so far, the specialization, so we can create a new class that inherits from the existing class, add new member functions, data member to it, and replace methods, which is actually kind of referred to as specialization. So we're going to go through a little inheritance example next to make different types of Z3s, essentially. So the class is organized in terms of a class hierarchy, as they call it before, which we've seen so far. With the superclass, the subclass, there's a lot of repeat in this lecture, so that's why I'm kind of going through it kind of quickly. Subclass is a superclass, maybe also a superclass. Now this is where the term reusability comes into place, because instead of reinventing the shape, a shape's a shape. We don't have to reinvent that every time, so we reuse it, and we just inherit from it. So we have the base, and this is essentially a repeat of what we just looked at a few minutes ago, so I'm going to kind of skip through it. But we can derive classes from shape as the rectangle, the circle, the triangle, so it's also a shape. So the car is a very general example of this. We can define a car called a BMW, and here we have a car, and then from car we've defined BMW, and we've added to it. So what did BMW get? The same information, but we added a few items to it, and then we can. We don't have to add any items to it anyway. We just make an instance of it and keep it as is. And then we can inherit. So in here, this example, we're going to inherit a Z3, and we're also going to inherit a 3 series. And this kind of demonstrates the lines of inheritance that are the capabilities that exist. So we might have some of the differences between the two classes, a number of doors, whether it has a roof or a hard top, and therefore the number of doors on the roof can be added to it. So here we go. So we have a BMW that comes from car, and then from BMW we have 2 other subclasses. One's a Z3 and one's a 3 series. The arrows are pointing in the direction of the inheritance. So Z3 and 3 series both come from BMW. So we have multiple classes that we can inherit from a single base class. It's generally going 1-to-1 though. Z3 comes from BMW, that comes from car. So the language itself supports a single line inheritance. But we can have multiple at each level. So we can have both a 3 series and a Z3. And what's going to be different is the roof or the sunroof or the no top, number of doors, maybe speed as well, I don't know. Engine size, maybe. We change the engine on it. So the views of the class, we have the inside view, we have the outside view, and we have the interface. And this is just the terminology review. And we have the implementation, which is the inside view. We have the public, the protected, and the private, which we've gone over already. So just to kind of add some summary comments to it. In most cases, public is dangerous to use. Private keeps things protected in inheritance. Protected makes things private to the public, but makes it public in inheritance. So in most cases, private is a very good way to keep the data members because it protects the integrity of the class. But in order to run the member functions, in order to get the class to behave, we have to make it public. So we'll see public methods and private data. And then we have private versus public in terms of the definition. I just went through this, so I'm going to skip through it. Protected, just went through that as well, so I'm going to skip through it. So we have special member functions as we've seen so far throughout the course, the constructor and the deconstructor. In Java, C++, the same. We have the constructor. It's a method that's called automatically when each new instance of each object is created. And it can set things by default, assign data members, values to members. The destructor is called when the object goes out of view, goes out of scope, gets eliminated. When does that happen? Kind of rare, actually. But we don't actually need to call anything on the destructor unless we are using dynamic memory. So if we're using new inside of the class, we're creating new memory inside of the class, we're going to use the destructor to destroy, to run the delete on the new, as we've seen with the pointers. In terms of accessing the data members that are available through each one of the methods, and we use that dot notation, just like the structure, as we've seen before. And in terms of accessing the class methods, we're using the same kind of concept on each one of the methods. Within the class method, it's just like a function, and outside of the class method, we call the reference to the object of the class, and we call that reference when we go dot the name of the function. So what happens here? We have the scope to consider. So each one of the, this is, which I is it, essentially, in terms of the class, we have an integer I, and then we have another function inside, and then we're going to print something out. Well, they're both going to be different, because they're in two different scopes, essentially. And the concept of scope is resolved in C++ with the scope resolution operator. So if we rewrote this line of code here that printed it out, and we prefaced which I we wanted, we would have to use this particular notation here to say foo inside of foo : I, which is giving us this I. Otherwise, we're going to get this I. So we can easily change the scope by using the scope resolution operator. Class scope. I call it the scope resolution operator. I don't even know where I got that from, but that's why, because it resolves the scope. Most textbooks call it the scope operator and leave out the word resolution for some reason. Makes more sense to put the word resolution in there, to me. Method names are done the same way, so sometimes you can put a prototype for a member function within a class definition, and then outside of the class definition you can add the specification for it, and you use the scope resolution operator to specify which method you're actually implementing. So here we have an example of that, where we have class foo, and inside class foo we have this integer sum, and this is in a .h file. And then out here in the .c++ file, we go integer foo, sum, sum, scope resolution to say, this is the function that we want to implement inside of this class. We're going to implement this function. I should really call it a method, but that's what we're looking at. Because we might have multiple, especially in terms of inheritance. We might have class foo that is inherited from class A or B or C, and then we can say A scope resolution sum, B scope resolution sum, and they would all be different. They would all be different methods, because everything is repeated in each one of the scopes. Doesn't matter, it's in a different scope, it's a different method. So that's how we can call different methods from different instances, different pieces of the object, and get the behavior to work for us properly. And just to review a little bit more, here we have the classes and the file system that's related to it in general. We could put everything all into one file, but normally we separate it out. Most people do this. They put the class definition in the class name.h, and any methods defined outside of the class definition, they put it in the .c++ file with the same name, actually. And C++ does not have the requirement that the file name has to match the class. So that can get kind of confusing, but it's a nice, good naming convention to follow Java and say, if you're going to have class foo, and it's going to be in this file, I'll call it foo.h and foo.c++. The .h and the C++ you need to put in there. Actually, the .h you can actually change. The C++ you need, for the most part. But the class name doesn't actually have to match. And it's kind of standard as well, now that I'm mentioning standards, to make that class name, make it a capital C in class, because you want to make the class objects capital, which is why we have string.h with a capital S. By default, the standard convention is to make it start with a capital letter, which actually follows through the same standard as Java as well. Looked at static methods today as well. The static method is a class method that can be called without having an object created. So it's running from the class implementation. And you use the scope resolution operator to identify the method that you want to run. And you can't access non-static data members from static members. It doesn't exist until you actually make an object, so you can't really access it if it's not there. Static data member, you declare the variable with the keyword static on it. So hopefully you'll take that concept away from today. And the data members that are static must be declared and initialized outside of the class. They can't be initialized inside of the class because they're static. They're only visible outside, so you can't use them through the instances. So it's at the global or the file scope when you use it. And here's an example again. We're hitting this concept home today. It's the same example we looked at before, actually. Static integer count. And so this would be called static to say that that one is going to be a class variable. So here's something new, friends. So a class can declare other classes as friend classes. Does not exist in Java. The class can declare external functions as friends. Friends can access the private members and the methods. That's what a friend does. So if you don't want to use the word protected, in inheritance sake, you use protected so that an inherited class can get at the private, so it treats private as public. You say, oh, the class is a friend. If they're a friend, you're breaking the rules of private again. Just like it protected. Except for now, you're just saying, okay, it's private to everybody except you guys who are friends. And the friends, they can access, and there's a little joke, but I'll save you on the joke. You can probably imagine what the joke is. Maybe not. There's an old C++ joke that goes around that says friends can, no, can't remember the joke. Friends can access the private members, I don't know. Anyway, something about private members. Anyway, long story short, if you remember private members, friends can violate the rules. You let your friends do it, but nobody else can do it. So. Your friend declaration here, you actually use the keyword friend class fee, and then we have friend integer print foo, foo, f. Well, you're getting at hopefully private. Everything's private in here. So if it weren't a friend, it'd come back with an error message and say, hey, it's not public, it's private, I can't do it, but you're a friend. So C++ is like that. If anything, it breaks a lot of rules, and nothing is consistent. It has a lack of, what do they call it, orthogonality. Not everything works the same way. And then if it does, well, we can put something in here like friend that doesn't exist in Java to say, hey, let's just break the rules. Okay. So. Okay, so we have two programming paradigms to actually kind of compare the structured procedural program with the object-oriented program to kind of recap, summarize the entire concept. Nothing more than functions out here. So if you're just programming with functions, you're not doing object-oriented programming. If you're programming with objects and everything is in an object, you're doing object-oriented programming by default. So. The features of the language, what makes it object orientation is that data abstraction, the concept of the object, the abstract data type, the inheritance of the properties, and the dynamic binding of the objects, operations to the objects. So, object-oriented programming terms versus C++ equivalents. The object is the class. Let me see, this is actually the same as Java. Instance variables are private data members. Methods are public member functions. Yeah, very Java-like. Message passing, you have a function call to a public member. So, what's an object? Oh, we know this already. Has objects, has operations and data that's associated with it. Actually, you can say an object is the identity, states, and behaviors. This slide's leaving out identity, but we have states, which is the data, and the behaviors, which are the operations that we're concerned with. Here's our inheritance among different vehicles. This, maybe I should have looked at this first and I would have known that vehicle came before car. Vehicle, we have boat. Wheeled vehicles, we have car. Wheeled vehicle, bicycle. Bicycle, yeah, it only has 2 wheels. This has 4 wheels, 4 doors, 2 doors, different types of cars. What you want to do is build your program like this. So you create identity for all the different objects and you build them together. Kind of, you think about it, it's kind of really different, I would say. Other styles of programming in a lot of different ways. So. We've seen this already. This is, again, another boring recap of a base class and a derived class as concept. And just to review the concept as well as the class time, our specification is our .h file. You know I'm going to ask you something on the final about specification and implementation files. Yeah. And you know I'm probably going to ask you something about inheritance. I'm probably going to ask you something about class members as well as instance members. Functions, variables that are from the class and the instance level, and about polymorphism, about inheritance, and reuse and stuff like that, encapsulation, information hiding. That's pretty much what the majority of the questions are going to be on object-oriented terms, and then I'm going to relate it to C++. That's what I'm going to do. So you're going to have to know how it's implemented in the C++ language. So hopefully it'll be very straightforward for you. So. Class time as a specification. This is actually not a bad review lecture for the final. But next week I'll tell you exactly what you need to know. Our class times is a .h file, and you might consider these function prototypes. Actually, they are. They're operation prototypes for what the class is going to do. And then when we make a class interface, we can have the public and the private. So the private's set out here. It's in the memory. And the public set of member functions to say the set, the increment, the write, and get the time, get the current time. And then we can use inheritance to add features to the particular time. In this example, we're going to set the time zone, extended time. And if you remember, the way we do inheritance is with a colon, space, public time. So I'm actually kind of thinking about maybe putting together some little examples with a, multiple choice. Shows you like a picture of a class or something, and then you have A, B, and C, This does this. This inherits one class from another. Or this is doing this. This is doing this. Or all of the above. Or something. Kind of a question. You're not going to have to write any source code, by the way. But you probably will be, hopefully, if I get creative enough, you'll be looking at some source code examples, maybe. But adding features, creating the extended time.h, where we go with the colon public time that's extended. Class extended time is inherited from public time. And that saves class time in a public base class of the derived class extended time. That's what this is actually doing. And it results in 2 objects. Every extended time is also an object of the time. So we have 2 objects in one. And then here's the what it would look like. Here's our 2 objects actually. We have the data that's associated with this one, the data that's associated with that instance, which is the same instance, same object. And then we have the 2 sets. So we get everything, actually. Here's the client code that we might use, and the client code is the driver program as well. Another terminology used for that, which is just main, essentially. Main's going to create some instances of the objects, send some information in to create this time, that time, and then essentially exercise the methods to increment the time, to write the time, stuff like that. We have some constructor rules on derived classes as well. As I mentioned, the default constructor, user-defined. Multiple constructors that we can create. We can create more than one. Same thing in Java. So at runtime, the base constructor is called first. So everything starts from the base and works up. So the base goes first before the body of the derived class constructor executes. All of the constructors will execute. So that's how we create an instance of time, and we also create an instance of extended time. So the object has 2 identities to it, actually. It's a time, extended time, but it's also a time. And both constructors will actually execute. So if the base class constructor requires parameters, then they have to be passed to it from the derived class constructor. And the parameters go down the chain to the base. So in the implementation of the default constructor, here we have an example where we have extended time that we're creating, and the default constructor doesn't take on any parameters. By default, that's the one that goes off automatically if you don't call one of the other ones. But it's a setting zone to equal to Eastern Standard Time by default. And then if we implemented another extended time class constructor here, we can say we have hours, minutes, and seconds, and time zone. And then we can inherit that from time. So we're taking time, hours, minutes, and seconds. That was the constructor initialization for the time object. We've added time zone. And so hours, minutes, and seconds were going to be passed to time so that that constructor can actually trigger correctly. So we just go backwards, inheriting through each one of the parameters that's needed for each one of the preset constructors that are going to trigger first. So we don't have to reinvent the wheel. If we already have a constructor that's setting hours and minutes and seconds in the time, we don't have to redo that. It's already going to set it for us in the default constructor for time. So in extended time, we just add the time zone to it. So it's already running, so we have the same body here with the zone that's being set. And then we have this method called set as an example, and set's going to set the time for hours, minutes, and seconds. And it's going to also include time zone because we're doing this in extended time. We're overriding set. So the time class would have a set method but would only work with hours, minutes, and seconds because extended time has hours, minutes, and seconds as well as time zone that's being used. And here's write, same concept as before, to print it out to the screen. We can set the zone string to all these abbreviations and then we can write it out. So. In terms of the composition or the containment, it's a mechanism by which the internal data or the state of a class includes the object of another class. So we say that extended time contains the object time because it's inherited from it. So we have a time card object that has a time object inside of it. That isn't inherited, it's just used inside. And here it is here. We have time card object. So, we have time card with time. Here's time down here. Time object is going to be having a time stamp. That's going to be the name of the time. So what we've done is nested or made an instance of another object inside of the time card object. So we have a time object in there. So it tells us we can have objects that have other objects inside of them, essentially. So we can nest the objects. And here's the time card class. So time card has a time object inside of it. These pictures are supposed to make it look like what it looks like in memory. But I've never actually seen what memory looks like on a computer, visually, like this. So this is a huge assumption that the memory would look like this. Although I think it would look at different colors if I were to imagine it. But I don't know where the author comes up with this stuff. The book is actually kind of hilarious when you look at some of the pictures. You know, that's how a pointer jumps. Oh, okay. Like, does a pointer really move like that? Does memory really look like that? I don't know. Doesn't really. Alright, here's the time constructor of the time card. In terms of this, we have hours, minutes, and seconds from timestamp. So the same concept works. If we created an extended time, put it inside of the time card object, we'd have time and extended time included in the same fashion. So we just nested the inheritance. It's the order in which the constructors are executed, just to review the concept, given a class X. If X is a derived class of the base class, the constructor is executed first. Next, the constructor of the member object, if there are any, are executed using their own default constructors. And finally, the body of the X's constructor is executed. So it's the reverse order. Starts with the base and works up through all the inherited classes. So in C++, when the type of the formal parameter is the parent class, the argument used can be the same type of the formal parameter or any descendant class type, which is interesting. You can create polymorphic behavior through this, actually, by sending it different parameters. So if you have different parameter lists, you can send it different parameters. You can send it 3, 2, 1, all floats, all doubles, all integers, depending upon the parameter type of what's defined in each one of the objects that are declared, that are being used inside of that one object. Static binding. So in a compile time language, the determination of the memory that needs to be used is usually done at compile time, and they refer to that as static binding. And when you pass by values used, you have a static binding that occurs as well, because you have the value that's being passed and not a reference. It's not like a dynamic which is the opposite of static, environment that triggers at runtime. So static binding and a base are a formal parameter type. We have anything that would be object-oriented that's using a class is always going to be a dynamic binding, because we don't know how many objects we're going to create until the program actually runs. We don't know what we're going to send. So here's our client code, here's our output, and our static binding is based on the formal parameter type, so we have time, some time that we're going to send to that function. So it's really a pass-by value, but it's actually treated pass-by reference because it's an object. And we have that object concept. I just talked about the virtual function, actually not too bad in the last lecture. There's a little repeat in this one here. So it allows a method to be overridden essentially in a derived class. So the time example, you'd like each time object to know which write method it wanted to use. So declare the base class write method virtual in this particular instance, and it happens that way. So. And as I mentioned, I don't know why this one's in there actually, but so the static binding, which is usually a pass-by value. The dynamic value is usually a pass-by reference kind of environment, or at runtime we were determining where we're going to locate these objects in memory, and we're actually kind of looking at the memory location in terms of the object. So in runtime, determination of which function to call and which object location for a particular object of the same class. So declaring a member function to be virtual instructs the compiler to generate the code and do dynamic binding. So, because then we have choices. We can call any one of the member functions from any one of the internal objects. So, and here's our keyword virtual that we're using for dynamic binding. So virtual, in some sense, this is new information actually, takes a statically bound method, turns it into a dynamic one. Gives us more options and more flexibility at runtime because it makes the classes and the instances aware of the different methods that might exist instead of statically binding them, making them permanent. So. And it creates a pass-by reference environment. Anything dynamic is pass-by reference. So. Using the virtual function in C++, dynamic binding requires pass-by reference when passing a class object to a function. Since you've got a function, you're going to pass a class object to it, an instance of this object. So at the declaration of the virtual function world, the virtual appears only in the base class. That means everything else that's created after that is going to be dynamically bound. So the base class declares a virtual function. It must implement the function, even if the body is empty, because it has to dynamically create it. And if it's not there, it can't create it, essentially. Because everything in the base is static. When you say it's virtual, it's still static. And then virtual says, hey, look for the dynamic creation of this method. Which is, even if it's empty, you actually have to include it. So, derived class is not required to re-implement a virtual function. If it is not the base class version, if it doesn't, the base class version is going to use it in a derived class. So. That was a quick review of everything we actually covered in this class in terms of the object-oriented components. The lecture after this is on recursion, as I mentioned before. You're not going to be asked any questions on recursion. It's not one of those, it's like a basic C++ concept, but it doesn't have anything to do with object orientation. So, questions? You guys are still awake. You've been trying to keep up with me all hour or so. I feel like I talked kind of fast today. Probably because this stuff is pretty boring because we've already gone over most of it. But that was a nice review lecture. Before some of you came in, I went over the assignments. All 5 assignments are going to be due. They're going to be due on August 16th. As I mentioned before, some of the assignments are in the lecture notes. You can find the answers to these questions or to the scenarios. The final exam for this course is going to be the third week in August. Let's take a look. The schedule is out. And for this particular class, it's going to be on 8/17. If you want to take it on 8/10, you can. I'm going to have everybody show up. Usually it's the opposite. Usually everyone wants to show up on the last week. They save everything they take it on the last day. But if you want to, beat the statistic, be new, innovative, you can take everything on the 10th if you want to. Or you can come on the 17th. It basically spreads it out, so you don't have to, if you're a student and you're taking more than one of my classes, you don't have to take them all on the same day. But for some strange reason, students like to do that. So, anyway, so this lovely weekend coming up, I'm going to be writing all of the exams Don't have any of them written yet, so don't ask me what's on them yet. So next week, I'm going to go over in every one of the classes what's going to be on the exam. So it'll be pretty easy. We're going to run through types of questions. So if you show up, or I'll purposely label the video so it says Final Exam Review on it, so you can easily find it on the website. And so if you missed the class, look for the Final Exam Review lecture. It will narrow down your studies so that you can figure out what you need to do. For this particular course, we didn't have I don't think we have a midterm. Do we have a midterm for this course? I think we did. We had a midterm, and we also had, hold on a second, we got a few minutes here. Let's see. We had those 5 assignments. Oops, there we go. So what else do we have going on here? We had a midterm, yes, we had a final exam. And a CSLO. CSLO is out there. If you can't find it on the EMS, look at it for bhacker.com. So everything's out there, so you should be able to do everything that's due on the 16th. Obviously, the final exam is going to be taken before the 16th. So, or actually, it gets taken on the 17th. Where'd that schedule go? Just had to schedule. Oh, it'll be due on the 17th. Well, most likely we're going to be changing that 16th to something. We'll leave it on the 16th right now. It's a good day to shoot for. So, but most likely it'll probably be moved a couple of days ahead, but don't count on it. So, questions, comments as we wrap up today? No? Then we're done for today. Next week we're into the final exam review. Okay, you're all done. You can go. Bye-bye.